graphs. So let me give you some transformations, right? So to consider. Before that, let's start off with this example. Sketch the graph of f of x equal to 1/2 to the x powered. Make sure to state the domain and the range. And range. Also, label all intercepts and any asymptotes. So here are some things that we have to consider, right? Number one is, because this is an exponential function, the domain will be all real numbers, just like polynomials. That's automatically true, since f of x is an exponential function. We get the following automatically. Number one, the domain will be all real numbers. We're also going to say that it will have a horizontal asymptote, right? It has a horizontal asymptote. But this is true because it's an exponential function. So let's see if we can start talking about this. What is another way to write out f of x as 1/2 to the x? We can write 1/2 as 2 to the negative 1, like this. You guys see it? And then we can use the exponent rules to rewrite this one as 2 to the negative x. So you can think about the original function as 2 to the x, the one that we had over here. And what do you do to this one? What transformation do you do to that one to get this one? Yeah, that negative there tells you that you reflected this about the y-axis. Yeah. So if you think about this as the original function being f of x, or just 2 to the x, we are just simply making a transformation. One transformation is reflection over the y-axis. Nothing else. That's all we're doing. So when you reflect something about the y-axis, the horizontal asymptote does not change, right? Because if you have a horizontal asymptote here at y equals 0, when you reflect the entire thing over the y-axis, the horizontal asymptote is still going to be invariant. It doesn't change. So we say that just as a something to point out, the horizontal asymptote is, we call it invariant. Invariant, meaning that it will not change. It will just stay as it is.
How come the domain is always
All real numbers?
yeah?
Yeah. So think about it this way. If I give you an exponential function like this on a table, could you have continued giving me larger and larger values here?
Oh yeah.
And then in the other way as well. So you can go in both directions, right? Yeah. So same thing with this one. So for the horizontal asymptote here, what will be the transformations that will affect the horizontal asymptote? The ones that will affect the horizontal asymptote will be the shifting it vertically. Yeah. Shifting this horizontally will not change the horizontal asymptote. Only shifting this vertically, and after we shift this, maybe when we say that's the only thing that we are going to pay attention to here. So this horizontal asymptote will change if there is any vertical shift. In this case, there's only one transformation, which is a reflection over the y-axis. So let's see. Here is the y-axis and the x-axis. And we know that at 0, the value of the function will be 1. And this is how 2 to the x was, 2 to the x. What do we have to do to this one? We have to reflect this over the y-axis, so it will look like this. Now, before this one, it will look like this. And after this, it will look like it's settling down. Like this. But it never ever gets to be equal to 0. You're just getting closer and closer and closer to 0 with every step. So this is the graph of 2 to the negative x, or 1/2 to the x. Like that. And the original function, you can think about that as this one right here. This is 2 to the x. And what do we do with 2 to the x to get to the other one? All we had to do was reflect 2 to the x over the y-axis, and that's what we get over here. It turns out that there is a little function later on that lives, I'm going to erase this, right? That lives between the two of them, like this one. Asymptotic to these guys, like this. Ouch. Let's see. Yeah, it turns out that there is this little function that lives asymptotic to both of them, like this. Like this. Like that. There's a little function. We call that function the cosine hyperbolic function. It just happens to live there between the two of them, which is really nice. But and it comes from exponential functions. That's how we define the hyperbolic trigonometric functions. But for now, this is how it is going to look like. Do you agree with me that the domain will be all real numbers? Yeah. So domain, just to emphasize that, will be all real numbers. The range now will be everything from 0 to infinity, exactly what it was before. The horizontal asymptote, what is this one now?
Still
Y equals 0, right? Yeah, the line y equals 0, like this, is a line. Yeah, and do we have any x-intercept?
Yeah, 1.
Yeah, the x-intercept. In this case, we don't have any x-intercept, right? But we do. Yeah, we do have a y-intercept and this will be 0, 1. I'm gonna write it like this. This is a point. You can just write out 1, but I want to make it a distinction between a point and the other one here. Y equals 0 is a line, right? The line there. That's just a line. Right? And usually we do this when we have a horizontal asymptote. I usually would do this. Mark it with a dashed line, telling you, hey, this is where y equals 0 is. This is the line y equals 0. Just to let you know that this is getting closer and closer to that. So if you want to write this out, you can do it, but you don't. This is not something that you should be okay with writing it down. As x goes to infinity, positive infinity, the function f gets closer to so give me a second, right? The function f gets closer to 0. Yeah. Okay. So your question is about the range, right? Yeah. Yeah. So you can get any y values or the output values. These are the collection of y values that you can get from this function, right? Your inputs are the x values, where the outputs can never be below the x-axis, so it cannot be negative, right? Because the graph is always above the x-axis. Can the graph ever be equal to 0? Will it ever intersect the x-axis? And the answer is no. That as far to the left as you can go, it will always be above the x-axis. As far to the right as you can go, it will get closer and closer to the x-axis, but will never cross it out.
So why can it be greater than 0? Like, can it be -1 to positive infinity?
No, I'm saying that it will never ever cross the x-axis. -1 will be over here, right? -1. The y value at -1 will be here. Will the graph ever be equal to -1? No, because it will never be below the x-axis. Not this one. Not this one. So as far to the right as you can go, the graph will just settle on the x-axis, but it will never cross it. It will never get on the negative side. There is no way that it can ever be -1. In fact, the only way that it could be -1 ever would be if you plug in a complex number. Then you can make it equal to -1 if you want to. But it will never cross the x-axis, so it will never be negative. It can never even touch the x-axis, so it can never even be 0. Right? So it's going to be from 0 not inclusive to infinity, like that. But just the y values, nothing else, right? Just that.
It's in the same So why there is no it's interesting.
It never crosses the x-axis.
Like C kind of crossed it.
Where?
Like at the right.
No, but I'm saying that it's getting closer and closer and closer to it. But the intention is that it will never cross the x-axis. It gets closer and closer to it.
Can domain be negative infinity to positive infinity?
Yeah, that's what we have here, domain.
Oh,
Yeah.
same thing. Right?
Same thing, yeah. Okay, so, and then as x goes to negative infinity for this one, as x goes to negative infinity, the function f goes to positive infinity, like that. Now let's take a look at another graph, right? We're building up, we're getting familiar with transformations at the same time we're building up some understanding of why the domain will be such, the horizontal asymptote and so on. And so here's our next example. Let f of x equal to -2 to the x, like this. So I want to sketch the graph of this function. Right. And again, just like before, I want to state the domain and the range. And the range. And finally, I want to label all intercepts and asymptotes. So before we had a y-intercept, and this was at the point 0, 1. I forgot to label that. There you go. So what will be the original function here? The original function will still be 2 to the x. What transformation do you do to this one to get the graph that you want? Reflection over the x-axis, correct? Because the negative is in front of this entire function, right? Yeah. So there's only one transformation, and this is a reflection. We can say over or about the x-axis. When you reflect this over the x-axis, right? How will the graph of this one look like? Well, this is it right here. Here is the original function, right? And it passes through the point 0, 1, and it looked like this, like that. On this side, it looked like this. like that. Now that we reflect this 2 to the x over the x-axis, now what will be the y-intercept now? It will pass through? Yeah, 0, -1, like that. And perhaps it makes sense that it will look like this. And for this side here, it will look like this. Like that. But it will pass through this y-intercept 0, -1. You see, I got a reflection of the same graph 2 to the x, but now reflected over the x-axis. So I'll get -2 to the x like that. So what will you say, right, will be the horizontal asymptote for this one? Yeah, will you agree with me that the horizontal asymptote will still be
0.
Yeah, 0. It's getting closer to 0 on the left side, right? Yeah. So this one here is still going to be the horizontal asymptote, like this. So this is the line y equals 0. And so let's write all of this out. So let's start with the domain. Maybe make this. Let's start off with the domain. And since it is a exponential function, it will be all real numbers. The range for this one?
From -1 to
From
from
0
to
to -2.
Well, we start backwards, right? From
-infinity to 0.
yeah, and we don't include 0 either because you can never even cross the x-axis, right? You cannot even be it won't cross the x-axis, so it won't create a 0. You will get close as possible to 0, but you're getting closer and closer to 0 from underneath, right? From -infinity. So the horizontal asymptote?
Y equals 0.
And I'm gonna write asymptote. This will be the line y equals 0. I'm just gonna write that there's a line. And the x-intercept, there is none, right? There is none. The y-intercept, there is one of them, right? This is just the point 0, -1, which is a point. Yeah, but this is what we have for -2 to the x. Now let me give you a other functions next to it, and then we can do a little more transformations on it, right? So consider this right here. So but this is where the problem ended. Here's a new thing. So imagine that 2 to the x is this guy here. 2 to the x. It passes through 0, 1. It goes up like this. On the left side, it goes like this. So this is 2 to the x. How will the graph 3 to the x look like?
We just cross at
3 to the x, when you plug in 0, it's still going to be 1. So it passes through the same point.
just go a little faster.
It's going to grow a little faster. When you plug in 1, you get 3 to the 1. That's going to be 3. The other one was 2 to the 1, which is 2. So to the right side of this one is going to be growing faster than this one. So this will be 3 to the x, like that. And on the left side of this one
Slightly
is going to go underneath it, like this.
It can be 3 to the power of -x, right?
No, just 3 to the x, but on the left side. Yeah. So it will be 3 to the negative powered, right? Because x on the left side of the y-axis will be 0.
I use
Negative.
cross 3 to the power of -x.
It will be a reflection of this blue line,
Y.
over the y-axis. Yeah.
Can you draw it?
Sure, if you want me to. Yeah. So here. So if we reflect this one, let me see. Over the y-axis, sorry, we will get something like this, like that. like that. So these will be 3 to the negative x, like that. Yeah. Yeah.
Man, why does it? Oh, I see. You flipped it, right?
Yeah, I reflected it. Yeah.
You flipped it toward the y-axis.
Yes. So there is a function that happens to be squeezed between the two of them, 2 to the x and 3 to the x. It's very special. We don't talk about it here, unfortunately. You ever heard of e to the x, right? That's the function that will be squeezed between the two of them. And so in the future, this happens to be a fascinating function. This is e to the x. It's a little bit closer to 3 to the x than 2 to the x because e has a value of about 2.718, right? E has a value of about 2.718, right? But again, it is a non-rational number, so we can't even tell you what it is. We can approximate that value. And it also happens to be squeezed between the two of them, like this. Like that. Yeah, just imagine there's some function is squeezed between the two of them. And there's a lot of very nice things about this function. But E is what we call this e to the x, we call this a natural exponential function, right? We call this the natural exponential function. And it turns out that it would be nice to be familiar with it, but that's something that you're going to discuss in 195 in pre-calculus, right? More in detail. For example, how do we get e to the x in the first place? We get this by compound interest. So you can do this every year, every half a year, every 4 months, every 3 months, every month, every week, every day, every hour, every minute. And the closer you increase these compounds, right, continuously, the more closer and closer we're going to get to this number e. And so it's a limiting value in it, right? But for now, just know that the e to the x is a natural exponential function, is a function that lies between 2 to the x and 3 to the x. But there's a bigger question yet, and we're gonna start talking about this after a few examples. Will these functions here, 2 to the x, 3 to the x, e to the x, all of these functions, will they pass the horizontal line test?
Yeah.
Yeah.
What does that mean? It means that
Is it 1-to-1?
it's a one-to-one, so we can find a
Inverse.
inverse. And we have, because this is a very common thing in mathematics, they decide to name the inverse a log function, right? And when you draw the two of them together, you're going to see that they're mirror reflections of each other about the line y cos x. Yeah, about the line y cos x.
So what's the function? Yeah, 2 to the power of x, right?
Yeah, so this one is 2 to the
Oh,
power
yeah,
x.
and you-
Yeah. So the base for these exponential functions, like the one on top that I just show you here, 2 to the x, its inverse will be a log, but it will also have a base, and the base for that one will also be 2, and it comes from the exponential function. So we're going to talk about that. For now, I want you to sketch this, right? Let f of x be equal to 2 plus 3 to the negative x. And I'm going to ask you to sketch the graph of f of x. Right. State the domain and the range. And also label all intercepts and horizontal asymptote. So what is the original function here?
3 to the x.
Yeah. 3 to the x. What will be the first transformation that it should go?
Around the y-axis.
Yeah, reflection over the y-axis. Yeah, reflection over or about the y-axis. What will be the second transformation? Yeah, shift.
Vertical shift.
Yeah, up by 2 units. So these one right here, number 2, is what's going to cause the the asymptote to change, right? So it was 3 to the x had a horizontal asymptote, but y equals 0. Now you're shifting everything by 2 units up. So now the horizontal asymptote will change, the range will change, right? Yeah. So it's good. Yeah. So now, if we are sketching this, we can start from the very beginning, but I think it's okay that we can just see how this is going to look like. So if we start off with 3 to the x, right, it will probably look like this. The original looks like this. Oh, let me try my best here. Like this. So this is 3 to the x. And what do we do first? We reflect this over the y-axis, and this is going to look like this now. Maybe. And this is like the first transformation that it goes, right? Or undergoes, yeah. The next one would be shifting everything by 2 units up. So the point that it was point of interest here was 0, 1. Now that will be shifted up by, so this is going to be at that point over there. So, and that will be the result that we get. So we're going to get something like this. Like this. This is the graph of the function that we want. And what is this going to settle to? It's not going to settle to 0. Well, 2. Because we're shifting everything by 2 units up, if including the horizontal asymptote. Yeah. So the horizontal asymptote, it will be now at the level where y is equal to 2. So let me just see. Yeah. And let me move this down a little. There we go. And break this up like this. There you go. So this is the line y equals to 2. That's where our function is going to settle to, on the right side, like this. To that line. It's going to settle to that. So what will you say the domain is for this one? Yeah, it's an exponential function, so it makes sense to have all real numbers. The range for this one will be
1 to infinity. 2 to infinity.
And not including 2, right?
Yeah.
So from 2 to infinity. Right. So that's good. Do we have any x-intercept?
No.
No x-intercepts, right? Yet. So this is none. It turns out that if you had shifted this 2 units down, it would have crossed the x-axis and it would have a x-intercept. But here, the y-intercept here is 0, 3, 3, right? And so 0, 3, and this is a point, and the horizontal asymptote for this case will be the line y equals to 2. This is a line, yeah. But that's what we get from it. So we start from the beginning, 3 to the x. It goes to under one transformation, and the second transformation gives us the graph. But it makes sense like that. Let's start talking about the next section, which is 4.3. Again, we are following. So if you have the booklet, right? At the beginning of the booklet, let's see. At the beginning of the booklet, we have this syllabus, right? And this is the from the mathematics department. And where we are right now is in 4.1. The next section here will be 4.3. And they even write a comment next to it, right? They say omit E and ln, right? Omit that. But in the pre-calculus, you will say that they will cover E and ln, right? They will emphasize that a little bit more. But for now we just have a few more sections which we should finish by the end of next week. So let's go back to this one. So in 4.3, this is going to be the logarithmic functions. Another way to say this, these are nothing more than the inverses of exponential functions. The inverses of exponential functions. So we're gonna talk about functions like this one, right? And I'm gonna write it like this. When we write y equals to log base a of x, when we write this out, we call this a log form, right? This is equivalent to an exponential form. And the exponential form for this one will be a to the y equals to x, like that. So it's like switching the y and x and ignoring the log, right? Yeah. So a to the y equals x, yeah. So it's like, makes a little sense, right? But this is what we have. These are equivalent forms, right? This and this, we're going to say that these are equivalent. And to get a sense of what we mean by equivalent, consider, for example, right? Consider this. What is 2 to the 5th power equal to? 2 times 2 times 2 times 2 times 2. 32. Can you write this in a log form?
Yeah.
Therefore, we're going to say, and how is this going to be? The base for this is 2. Yeah. Log base 2 of
32 equals 5.
yep, 32 equals to 5. Hmm? Yeah. So these are equivalent, right? And someone has to start with these ideas on how we're going to define this. And it's good to start creating a new notation. Y equals log base a of x, right? This is a brand new notation. You see how we write ln? If you go to Wolfram Alpha, for example, if you go to Wolfram Alpha and write ln of 2, what will be the base for ln? Well, the base for log, yeah,
2.7.
the number e, right? So ln and log are exactly the same thing. You just run under different bases, right? So if you put ln of 2, for example, last time, yeah, it's about 0.693. But if you enter this and read what Wolfram Alpha writes, what does Wolfram Alpha changes it to? Log 2. You didn't write log 2, you wrote ln of 2. It's saying, hey, this is just a log function, just evaluate it at 2. But it tells you this little warning on the right side. It tells you log here is used for the natural logarithmic. Right? So it's like we always are going to use log. Not in this class, pre-calculus and calculus, you write ln, but eventually later on ln is just a log, but it runs under a special base, right? That special base is e. So there's nothing wrong with changing ln to log. You just have to put the little warning there. Here is the base, here is e, but it's running on different bases, right? So if we write this out, right? Here's another example, right? If evaluate, right? And hopefully you have seen this before. Log base 10 of 1,000 equals to x. Evaluate this value here. I made it equal to x because whatever the value is will be some number x. So our goal is to figure it out what x is, because that will give us the value of log base 10 of 1000, right? But can we write this in exponential form?
Yeah.
In exponential form, what will this be? So 10 to the x equals to 1000. And 1000 is 10 to the third. So if 10 to the x equals 10 to the third, that you see how the bases are the same? Then x has to equal to 3. X equals to 3. And so it makes sense that, hey, log base 10 of 1000 equals x. The x value here will be 3 because 10 to the third will give you 1000, right? If you write it in exponential form, it makes better sense. Here is a remark, right? And you are familiar with this remark, right? When we write log base 10 of x, we don't want to waste our time and write 10 underneath this. We are going to write this log of x. We don't write anything there. When we don't write anything there,
It's the mean base 10.
yeah, by default, we're going to say that the base is 10. We call that the standard base for logs, right? 10. Let's take a look at a log function, right? And then I'm gonna say, have you ever heard of logarithmic paper, graphing paper, logarithmic graphing paper? Right? So instead of having 0, 1, 2, 3, 4, the thick marks on the x-axis, is going to have 0, 1, 10, right? 10 squared, which is 100, 10 to the third, 1000. So every single thick mark will be, the way that we measure sounds, for example, is by decibels, right? And from one unit to another one, it's not just, it could be doubled, right? Even though it's from 12 decibels to 13 decibels, it's 1 decibel difference, but this is an exponential, right, form that they're representing decibels. So if you are 12 to 13, there's a huge difference between the two of them because the difference is exponential. Anyways, here is our question now. Let f of x be equal to log base 2 of x. How is this going to look like? Sketch the graph of f of x. The graph,
Just 2 to the x.
yeah, of f of x. And the way that we're going to do is we want to state the domain and the range. And range. And we want to label all intercepts and asymptotes. And the way that we're going to do this is, let's consider f of x here, what we're given, log base 2 of x. And on the other side, the left side, we're going to consider the exponential equivalent of this one. Equivalently, not equivalently, sorry. Yeah, we're gonna write another function here. Consider the function an exponential function. The base for that log is going to be 2. The base for this exponential function here is going to be 2 as well. So we're going to take a look at the function 2 to the x. And imagine that this is y equals 2 to the x. That's our function. What will be the equivalent form on the right side? The equivalent form on the right side. Yeah, equivalently. What will be the equivalent form of this log? Yeah, so we have y equals log base 2 of x. That's what we have here. Y equals log base 2 of x. We can write this as an exponential, right, function as, right, 2 to the y equals x, or x equals 2 to the y. So what is the difference, or this one right here, the one that I box on the left side and the one that I box on the right side? they're inverses of each other. So if we want to graph log base 2 of x, all we have to do is get the graph of 2 to the x and reflect it over the line y equals x, and we get the image that we want. That's how it will work, right? Of course, it's not always the case that we're going to do this all the time. We're just going to memorize how this looks like, right, in the future. So these are inverses of each other. So by that, they're going to be mirror reflections of each other about the line y equals x. So here we are familiar with 2 to the x. And I'm going to label everything that we know about this. So here is x. I'm going to shift this a little. And it passes through the point 0, 1. And this one, right, it looks like this one. Ouch. And on the left side, it looks like this. Ouch. Like that. So it passes through that very special point. Okay, let's label everything that we know from before, or write out everything that we know. What will be the domain for this one again? All real numbers. The range for this one? It has a horizontal asymptote. This is the line y equals 0. This is a line. And we also have a y-intercept.
I think there's also a vertical asymptote.
Not for the left side, no.
But the right side there is a vertical asymptote.
Correct, yeah. So the y-intercept will be 0, 1 for the left side here. And this will be a point. But this is good enough, right? Now, every single thing is going to affect the right side now, because we're going to reflect this about the line y equals x, like this. Let me just write it like here. Yep. And let me cut this out like this. Oh, man. We're going to reflect this about this line, y equals x. And that's how we're going to get the other image on the right side, right? We're just reflecting this. So how is this one going to look like if we reflect this about the line y equals x? Let's see what graph we're going to get. So the point that this left graph passes by is 0, 1. Where is that going to go on the right side?
0, -1.
Reflect this about the line y equals x, and you're going to get 1, 0. Yeah, over here. So this point on the left side is going to be now this point on the right side. And let me know if this makes sense. To the right side of this one, the right side of this one will look like this. Yes? To the left side of 1, what is it going to get closer to? Before, this one was getting closer to the x-axis.
Close to the y-axis.
Yeah, it's going to get closer and closer to the y-axis like this. And those, it will create this little effect there. So it's getting closer and closer to the y-axis like this. So we have a point on it, 1, 0. And so far, this is the graph that we have. Let's talk about the domain for this one. What is the domain for this one?
It's from 0 to infinity.
Yeah, do we include 0?
No.
No. And what about the range for this one?
All real numbers.
The range for this one will be all real numbers. If you notice on the left side, the domain was all real numbers and the range was 0 to infinity. Because you switched the x and the y, they switched, the domain became the range and the range became what the domain was. Because you switched the x for y and the y for x, that's how we got the inverse for this one, right? So guess what happens to the horizontal asymptote then?
The vertical.
Yeah, and it will be the line x equals to?
0.
Yeah, x equal to 0. So let me just put this here. Make this here. So these right here will be the line x equal to 0, and this is a vertical asymptote now. Vertical asymptote. Is x equals 0, and this is a line. And the y-intercept here now gave us a x-intercept, and the x-intercept is just 1, 0, and this is a point. From here, we can shift this up, down, left, and right. And what will affect the vertical asymptote of the log function? Only if we shift things to the right and left.
Right, left.
Yeah, if we shift this up or down, this is not going to affect the vertical asymptote. Let's do one problem and let's call it a day, right? So here's an example. Let f of x equal to, right? Say 9. 9 is good. Yeah, 9 is good. 9 minus the log base 3 of x. F of x equals 9 minus the log base 3 of x. And I want to sketch the graph of f of x. And using transformations will be ideal, right? State the domain and the range. Also, label all intercepts and asymptotes. So let's start off with the transformations. The original one, right? Original. What would it had been? It would have been 3 to so log base 3 of x. What is this? To get familiar with this one, this is nothing more than the inverse of 3 to the x. This is the inverse of 3 to the x. It's an exponential function, so we know how 2 to the x looks like. This is identical to that one, right? But this is the inverse of 3 to the x. What is this going to undergo? What transformations will it undergo?
You rotate around the x-axis.
Mm-hmm. Reflected about the x-axis. And number 2,
9 to the left.
yeah, it will be shifted 9 up.
Oh, up.
Yeah, shifted 9 units up, like that. So let's see if we can imagine how this one will look like, right? I'll give you the original.
Can you convert? Can I convert it into exponential and then plug it, because that would be much easier.
Yeah, the exponential you can convert it, but then the exponential will give you backwards. It will give you like x equals in terms of y. So you have to rotate it around. If you graph it in y because a function of x, right, then you have to reflect it as well, right? So, but we know how this one will look like, 3 to the x. So how is the log base 3 of x going to look like? Identical to what we had before. So this is the original. The log function for this one. Let me just fix this a little. The log function will look like this, the original one. So it passes through this point. After this is just going to look like this. Before this one is just going to get closer and closer to 0, like that. This is the original log base 3 of x. It passes through this point 1, 0. The first transformation that this is going to undergo will be reflecting this about the x-axis. So how is that going to look like? So this one will look like this. So it will look like this. And this part right here will go like this. If Maybe I can do this a little bit better. Do you see that's a reflection of the original? This is the first transformation that it undergoes. What about the next one? Everything will be shifted up by 9 units. So this point that we had there is the point 1 0. Where is that going to go? 1 9th, all the way to 1 9th. So just imagine 1, 2, 3, 4, 5, 6, 7, 8, 9th. There's 9th. And this is where the point is going to be. Like that. So how is the graph of this one going to look like?
Way up there.
Yeah. So it's going to look like the second line, the second line that is sketched there, but it's going to it's going to look like this. Let me just put it solid like this. Ouch. Let me see if I can do this better. It keeps on going like this forever, and you're just gonna keep on doing this really slowly. Let me just copy all of this in another page. Yeah, copy. There's some things that are not gonna be moved. Yeah, and yeah, I'll emphasize some other things. This is gonna get closer and closer and closer and closer to the y-axis, probably like this. Yeah. There was a point in it, right? There was a point in it that was very special. That was the 1 comma, not 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, this one right here, 1 comma 9th, and it will cross the x-axis. Will it ever cross the y-axis?
No.
It will get closer and closer to it, right? But it will cross the x-axis. Do you guys have any idea when it will cross the x-axis?
10?
Nope.
9 to the 3rd.
So let's see. Let me just imagine that this will continue like this, right? Slowly. Here's the x-axis here. Yeah. And it will cross the x-axis, and you have to use your imagination for that. Whenever y is equal to 0, right? And we had this 9 minus log base 3 of x. When you set this equal to 0, you have 9 equals to log base 3 of x if you add that on the other side. And you can write this in exponential form as 3 to the 9th equals to x. That's this guy here. That's what x is. 3 to the 9th, comma 0. That's a huge number. So sometimes when you have a graph like that, people do this in the graph like this, to use your imagination that there's going to be a huge difference between them, but it's going to be a big number.
So if the question asks to point out the x-intercept,
Mhm.
how would we do that?
I just did it there.
Just do that?
Yeah, that line just tells you that there's going to be a big difference between that. In physics, they usually do that when they graph a line, and they put a swiggle line in between, telling you that there's going to be a lot of numbers in between missing.
You can just write 3 to the 9th power,
Comma 0, yeah. But anyways,
Okay, what's the range?
yeah. So the range for this one, what do you guys think the range for this one will be?
All real numbers.
All real numbers.
How?
We talked about log and exponentials. For exponentials, the domain was all real numbers. The logs are going to be the inverses of that. So the range, the domain for this one will now become the range for that. All real numbers. You can go as high up there as you want to, and as low as you want to. But the x-axis, the x values are going to be restricted. Anyway, so let us give you back